Now that we understand how RSA works, we are going to look at how SSL, which is called Secure Socket Layers, we're going to look at how SSL makes use of RSA keys in the cryptographic exchange. So on the left-hand side here, we have a client, and on the right-hand side, we have a server. So we can think of us as being the client on the left. That's just us on our laptop or mobile device or home PC or tablet or something like that. And on the right-hand side, let's say it's a web server. So maybe we're trying to access Amazon.com. So those are Amazon servers there on the right. The first step we refer to as the client hello step. So the client is actually going to list the crypto algorithms that it supports. Now there's a whole long list, so I'm not going to go through them here. Literally just a list of algorithms that are supported by the client. But if you're interested, please let me know and I can point you to that list. The second thing that the client does is it generates a random number. So we'll call that random number number 1. And it's going to hold on to that random number for the time being. So it sends the list of supported algorithms over to the Amazon web server. The Amazon web server takes a look at that list, looks at which ones it supports, and then chooses probably which one is most cryptographically safe, so the most secure algorithm in most cases. Then what the server is going to do is it's going to generate its own random number, which we're going to call random number number 2. And then the third thing it's going to do is it's going to take its SSL certificate, which we'll talk about specifically what an SSL certificate is in a couple of slides. And it's going to send the random number number 2 and that SSL certificate back over to us, the client. And this is where the negotiation step begins to take place. So the first thing that the client's going to do is it's going to take that certificate and it's going to verify it. And we'll talk also in a little bit about specifically what the verification process entails. But basically, it's going to take the SSL certificate and verify it with a third party. And the SSL certificate is basically going to say, okay, indeed, it appears that this person's identity is Amazon. So you can trust that using that public key, you're going to be communicating with Amazon. So that's fine. And in theory, the way the public and private key works, the public key of Amazon can be distributed to anyone as long as Amazon keeps the corresponding private key completely safe. So the next thing that the client is going to do, it says here they encrypt the pre-master secret. So the pre-master secret is going to be the client is going to take the server's public key and it's going to encrypt random number number 1. And it's going to take that encrypted result of random number number 1 and it's going to send it back to the Amazon server. Again, in theory, it's okay if other people see the exchange since it's encrypted. They should not be able to determine what random number number 1 is. So that encrypted message arrives back at the server, and as you can see, Amazon takes its private key and decrypts that message to get the pre-master secret, which again, that's just random number number 1. So now we were able to securely transfer random number 1 over to Amazon. So now Amazon is holding random numbers 1 and 2 at this point, and we're holding random numbers 1 and 2. Okay, but no one on the outside knows number 1 because we didn't transmit it, and no one on the outside in theory should know number 2 because it was transmitted in an encrypted fashion. So now we share this pair of secrets, secret 1 and secret 2. We have a copy of both of those, and so does the Amazon web server now. Okay, so in step 5 here, you see that step 5 happens in parallel on both sides. Now that we both have the pre-master secrets, random numbers 1 and 2, we perform some function. It could be just appending the two together. It could be an XOR of the numbers. It could be some relatively simple mathematical function. And then we're both going to be left with the same shared key as long as we compute the same function on those two inputs. Okay, so at this point, once we both do that, we have what we call either a shared secret or sometimes referred to as it's a symmetric session key. At that point, we're more or less done. So the important distinction to see here, you see the blue line drawn across the diagram. Everything above that line, notice that we used public key cryptography. So we use the idea of public and private keys to exchange the random number information with the server. And at the bottom, underneath of that blue line, notice that we now have a shared secret session key. So everything above that line is referred to as asymmetric cryptography. In other words, a public and a private key were used for that exchange. And now everything going forward below the blue line is always going to be using that shared secret key to communicate. Okay? So the reason this is interesting is because from a theoretic perspective, asymmetric key crypto is actually a bit slower than symmetric key crypto. So we use the asymmetric key method up front to exchange random information. And then once we've done that, we simply go ahead and compute a shared secret key for each of the steps. We'll use that for each of the encryption steps going forward because it's much, much faster in practice. So hopefully that's clear. Again, everything above the line, asymmetric key crypto. Everything below the line is symmetric key crypto because symmetric key cryptography is much faster. This slide here just kind of talks a little bit about what we said on the previous slide and leads us into the next couple slides we're going to cover here. Just generally, what is a digital certificate, in particular an SSL digital certificate? The digital certificate, as we mentioned, just simply binds a public key to the owner of that key. So what does that mean exactly? Usually it's some sort of maybe a third party, and what they'll do is some sort of verification process. Well, they will either issue a public key or take your public key from you and perform some kind of verification step. It could be online, it could be offline verification. Okay, but either way, they take your identity and they link it to a specific public cryptographic key. And these certificates are issued by something that we'll call a certificate authority or a CA. You'll see a list of these guys on the next slide, but VeriSign and GoDaddy are some of the top two that come to mind, the major certificate authorities that are out there, of which there are a relatively small number. And the other important thing that a CA does is it maintains something called a CRL, which is a certificate revocation list. And this certificate revocation list, so in addition to telling you who owns which keys, the revocation list also tells you who it's not safe to trust. So we'll talk a little bit more about what the CRL gets you in the upcoming slides. What specifically then is a certificate authority? As we touched on a little bit, we said that the certificate authority is a trusted third party who's responsible for both the issuance as well as the revocation of different types of digital certificates. Again, remember, a certificate simply links someone's identification to their private key so that when we get that private key, we can know the person on the other end is who they claim to be. Now, there's two main types of digital certificates. One of them is a client certificate. That is something that we probably have in our browser. Okay, and then there's also a server certificate. So borrowing from the SSL example we saw 2 slides ago when our client was communicating with Amazon, remember the first step, we went out to Amazon and queried them for their public key certificate. And so what they respond back with is their signed server certificate. Okay, so the two main types are client certificates and server certificates. And then thereafter, so for both a client and for a server certificate, there are different parties who can sign them. So one thing that we can do is go to a trusted third party, and you can see a list. You probably recognize a lot of these, or you recognize them as large hosting providers, or you've seen their names in the news as being large certificate authorities. So one thing we can do is just go to any of these people and pay something, maybe a $20 annual fee, roughly something like that, and they will issue a certificate to us. That's not necessarily required though. So the other thing that you're free to do is you can install a library. So on Linux, the common one is OpenSSL, and you're free to stand up your own certificate authority. And what you can do is you can actually issue certificates to yourself. And when you do that, we refer to them as self-signed. Okay? So major difference there. And there are use cases for both of them. So for example, the trusted third party certificate is good because if we decide to run our own website, right, and we're hoping to generate revenue through online sales, let's say, it's going to be difficult for us to get people on the network or people on the internet to trust us. We don't have the same reputability as a lot of these large CAs do. So it makes a lot of sense for us to go ahead and reach out to a Thought or a Semantic and grab a certificate from them. Because then what the people shopping online can do, they visit our website, they get our certificate, our server certificate, and then they take it and they're going to go back to that trusted third party who issued it and say, hey, is Joe's store actually who he claims to be? And then Symantec is going to say, yes, you can trust this person. Or if someone's posing as us, they're going to say, no, you cannot trust this person. We did not issue it to them. And then that person can decide whether or not to proceed with the transaction, whether or not they get that lock, the locked lock in their browser. So obviously a self-signed certificate wouldn't work too well in that case because people don't trust us. So when would a self-signed certificate be good? Well, let's say you set up your own infrastructure for a 100 or 200 person company. So you set up your own Active Directory, let's say, and you want to be able to issue certificates to each of your users within your infrastructure. Well, if you're the trusting authority, you know that you're the one issuing certificates. And of course, you trust yourself. So if you want to give self-signed certificates out to your employees, that's going to be completely okay. There's no reason to go to a trusted third party when you are the certificate issuer. You don't have to spend $20 per employee when you can just sign your own certificates because you know that all those certificates were issued by you. So within your own organization, it's probably a little bit easier and much cheaper to use a self-signed certificate. But when you're trying to get people outside your organization to trust you, you're probably going to want to go that third-party route. And something you've probably heard before, Hopkins also offers a course in this, is public key infrastructure. The certificate authorities are one of the main components of a PKI. And there's basically a tree structure in place. And don't worry, we're not going to go too deeply into it. But I just wanted you to see these terms, that at the top of the tree, there is a root certificate authority. And that certificate authority may issue tickets to a select number, call it maybe 5, 10, a dozen of intermediate certificate authorities. And then each of those intermediate certificate authorities, may sign certificates for an issuing CA at the lowest level. So you've established this sort of tree of trust. And then it's those issuing certificate authorities at the lower level are the ones that we communicate with to purchase our third-party trusted certificates. And the other main job, in addition to issuing certificates, as we said, the certificate authority is also responsible for maintaining a CRL. Okay, so the CRL is a list of certificates that have been revoked. So, let's say, for example, that we have an entrust certificate for our website, and let's say we were careless and our private key became compromised. So we no longer wish to have a certificate that binds our public identity to the corresponding public key, because we know that someone out there could be posing as us because they have the private key in hand. So in that case, what we're going to want to do is, first thing we're going to want to do is shut down that existing key pair. Okay, so we're going to reach out to Entrust and we're going to say, hey, please revoke this certificate. It looks like our keys were compromised, so we don't want to use them anymore. And so what they're going to do is add us to their certificate revocation list so that the next time someone tries to visit our website, they get our certificate, they go to check it with Entrust, and Entrust says, oh, wait a second, you cannot necessarily trust that the person on that endpoint is the company that it was intended to be because they're listed with us as having been revoked. Okay, so this certificate revocation list is also maintained by the certificate authority, and we will talk a little bit more about the details of it in the upcoming slides. Next, we're going to look a little bit more at the anatomy of one of these SSL certificates. So you can see here I've given an excerpt of a sample certificate This is actually from a Windows certificate store, so the interface and the image there might look familiar. And I just want to talk about a little bit about how the verification process takes place. So think back a few slides ago to the SSL exchange that our client did with the Amazon web server. In step one, we sent traffic to the web server, and the first thing we did, in addition to generating that random number, we requested that Amazon send us a copy of their public certificate, of their SSL certificate. Okay? Again, it only contains their public key, so it's perfectly safe for Amazon to go ahead and share this with the world. Upon receiving that, we're going to want to validate that certificate. So the first thing we're going to look at, unfortunately I have them a little bit out of order here. The first thing we're going to look at is the issuer field. Okay, so the issuer is going to tell you which certificate authority was it that issued this certificate to who we think is probably Amazon. Okay, so that's what we're going to start with. We're going to say, who is the issuer? And then what we're going to do is look inside the browser, in our case, and say, first of all, do I have this issuer in my list of trusted certificate authorities? So if the issuer is Bob's Certificate Shop, no offense to Bob, but maybe that's not as reputable as VeriSign or GoDaddy in our opinion. So it's unlikely that Bob's Certificate Shop is going to be in our local store of trusted CAs. But if we see something like Thought or Entrusts or VeriSign, we're going to say, okay, well, I generally trust this certificate authority, so I'm going to investigate further. Okay? So the next thing we do is we're going to check what's called the CRL distribution points. So since we trust, let's say the certificate was issued by VeriSign, since we trust VeriSign, we're going to take a look at the CRL distribution point. And what that tells us is where we can go, maybe it's a website, maybe it's a web service call or something like that, to download the most current certificate revocation list. So where can I get the CRL from? We're going to go to that location and download the most recent CRL. And we're going to take the certificate that we currently have. Okay, it has a serial number attached to it, a unique ID. And we're going to say, okay, does this certificate that Amazon just sent me, does it exist on the most recent copy of VeriSign's revocation list? Now, obviously, if it's on there, we have issues, and we probably don't want to proceed with that website. We probably don't want to proceed with our purchase in an unsecure fashion if the certificate has been revoked. But if we look for that certificate on the CRL for VeriSign, and we don't see it there, that means it hasn't been revoked. So we think, for now, that this certificate looks roughly trustworthy. Okay, so now we're going to proceed to the next verification step. And what we're going to do there is look at the valid from and valid to field. And naturally, we're going to take a look at the current timestamp and the current date, and we're going to make sure it's both after the valid from period, but before the valid to period. So it's very possible that, the certificate may have gone out of date just a minute ago, and maybe it didn't pop up on the CRL yet. Okay, so this is an additional way for us to be able to validate based on date and time. So we're just going to make sure that the current time is between the valid from and valid to that are listed in the certificate there. Okay, and once we've done that, we can roughly assume, okay, we trust VeriSign, number one. The certificate was not a part of a CRL, number two. And VeriSign's telling me it's valid from this date to this date, and I'm currently in between that time window. So 3 for 3, I think I'm going to go ahead and I'm going to trust that the public key listed in this certificate does indeed belong to Amazon. Okay, and again, if we didn't trust the issuer, if the certificate appeared on the CRL somewhere, or if the valid from and valid to date have expired, then those are 3 reasons why we might want to not trust it. Otherwise, we're going to go ahead and assume that the public key that we're going to encrypt our random number with is indeed suitable and safe for use. The final thing we're going to talk about is just a little bit more detail on the certificate revocation process. Remember what the CRL is used for. It's used to keep a list of certificates that have been revoked by the certificate authority. Okay, but I wanted to specifically point out some of the reasons that a certificate might become revoked. So when you look up the CRL distribution point listed in the certificate, okay, it's going to give you the location of the most recent CRL. You're going to pull the CRL down, and let's say that in fact you were trying to access Amazon, but for some reason the public key certificate that you got from them is on their CRL, is on VeriSign's, let's say, CRL. Within that CRL, you're going to have the unique serial number of that certificate, and along with some other information, you're going to have a reason code. And I just thought it might be useful for you to see some of the reasons that a certificate can be revoked. Probably one of the most common ones we see, unfortunately, is unspecified, which is just a code of 0. The RFC, which, by the way, I've included a link to the RFC right there. So RFC 5280 is actually the RFC that specifies in super duper great detail how the CRL process should work, how the field should be specified, what each field means, what the CRL extensions are, so on and so forth. Well, by no means do I recommend you take a look at it and read the whole thing, but if you're interested specifically in what each of these CRL reasons mean, or what any of the extensions in the SSL certificate itself mean, there's a pretty good rendition of that at that website, so feel free to take a look. But as you can see, there's basically 2 states for a certificate. One of those states are revoked and the other is on hold. Now, it's important to know that a revoked certificate, once it's revoked, it can never be used again. So it's a revoke operation of a certificate is absolutely permanent. And then the difference between that and the hold state is actually not permanent. So, for example, if we look at CRL reason number 1, so a certificate can be revoked, as we said earlier, if we believe that the public key was compromised. But let's say we're not sure if the public key was compromised. We only think that maybe it was, but we're in the middle of an investigation internally. But in the meantime, we choose not to want to temporarily revoke our certificate. So we can actually contact the CA, and they can put us on the CRL with a state of hold, which is basically a temporary revocation. So it might be the case that we do some internal investigation and we determine that the private key was not compromised. So we don't want to have to go ahead and reissue all new certificates, right? So we want our certificate to be removed from the CRL. So a hold state allows you to temporarily revoke, and then from there, you can either make the decision that the certificate can still be in use or it should be revoked outright. So CA compromise, so CRL code number 2. It's certainly possible that we did nothing wrong, and maybe the certificate authority itself somehow suffered a breach. Either they were hacked externally or maybe there was an internal leak. But if there was an issue at the CA, there's a chance they may have to do a bulk revocation of the certificates that they've issued. In that case, you'd see them all show up with a code of 2. So there's a number of them, and you can look through them. Superseded, it's certainly possible that we just decided to get a new certificate for some reason. So we're just invalidating our old one and decide to use our new one. So that's when we would use superseded. And so feel free to take a look at the RFC if you're interested in more of the details, but just wanted you to see some of the common reasons why certificates get revoked and the codes that they use on the CRLs. So hopefully you enjoyed the first week. I definitely enjoyed the lecture. This is a brand new lecture series this semester. Just kind of wanted to take you through from some of the mathematical beginnings of RSA, show you how RSA is used as the algorithm of choice in the SSL exchange. And then once SSL takes place, I wanted to show you a little bit how certificates are issued and revoked if need be. So if you have any questions, always please feel free to email me. I'm happy to chat with you about anything, and thank you for watching.